All right, I want to return to VSEPR theory and talk about some of the less common, higher order molecular geometries that involve more bonding groups. So to remind you, VSEPR had rules, right? Electron domains, and that meant bonds. Couldn't care less whether they're single, double, or triple. And lone pairs. Spread out as much as possible because they don't want to be close to one another. They want to reduce repulsion. And lone pairs and bonding groups, because they're trying to reduce repulsion, take up similar amounts of space. And in fact, a lone pair took up a little bit more, and we had some scrunching on bond angles. What we need to think about with these higher order geometries that we're going to see is that every atom that you're going to see going forward is going to have an expanded octet. So you're going to count those up, and you're going to see that, crap, that number has, or that central atom has 10 electrons or 12 electrons. We don't care, because remember, if you're in the third period or below, you are an element that can expand your octet and take on more than 8 electrons. And that was okay, because if we went back and calculated formal charge, we saw that the formal charges would go down to 0 when we expanded the octets. Formal charge is a better indicator of a good structure than octets. So remember this table that I suggested you make in the last video about VSEPR? Still not kidding. Pause the video, get out that table, and you're going to add more lines to it. If you haven't made that table, pause the video, make this table, go back and watch the old video, please, and write it out, and then add this stuff to it. Just like last time, hybridization is a topic for another day. You'll fill in this table with information you get in other videos. All right, 5 electron domains, and this is a fun one, right? The main name for this is trigonal bipyramidal. So trigonal, there's going to be something triangular in here, and bipyramidal, there's going to be 2 pyramids. You cannot see that in any of these structures that I drew down here because they're flat Lewis structures, right? PF5 and SF4 and ClBr3 and I3 minus. They all look flat, and I could draw in the lone pairs that are missing. But again, that doesn't fix the fact that this is a flat board and real molecules are 3-dimensional. So we want to think about what that would look like. So 5 bonds and 0 lone pairs is called trigonal bipyramidal, and you're going to see, because there's a triangle and a pyramid, that there's 2 angles that go on. There's a central atom, and I'm going to call it X. And there's 3 elements in a triangle around the middle, so it's like trigonal planar, right? There's one coming out of the board, and there's one going back into the board, and then there's ones up and down. And I'm going to draw those ones that I just put up and down in a different color. Because what we actually have, and this is going to show up in 6 electron domains as well, these red ones are what we're going to call the equatorial atoms. So we've got the atom in the middle, and then it's like they're arranged around the equator, right, around the globe. And then the ones that are going up and down, we're going to call axial. And that's how we get multiple bond angles, right? That's how we get a bond angle through the center, through the equator. That's 120 degrees. Here's another 120, and here's another 120. And I'm going to draw this again so that I can put in the other bond angles. And the 120s we've drawn, but the 90s are axial to middle to equatorial, right? So around the equator, you get 120. But down the axial, you get 90. And again, the presence of lone pairs will squish those angles a little bit. So in SF4, we'll see in a little bit where the atom comes from. Is it going to come off of the equator, or is it going to come off the axial? So we'll get a look at that. But the remaining angles are going to squish a little. And they're going to keep squishing as I go down, right? Less than 90, less than 120. And by the way, once we get down to here, straight up 180. We'll see that in a little bit. And in fact, these just end up all being 90 as well. We'll have to draw that. But the names for them are easy and kind of cool. And when you see the shapes on the next slide, it'll make sense. Trigonal bipyramidal, seesaw. That's this molecule right here, where I've got 4 bonds and 1 lone pair. T-shaped. Doesn't look much like a T on this flat page, does it? But we can fix that. And then what's left when I take off and make 3 lone pairs and 2 bonds is a straight line, right? So memorize those bond angles and what those mean, and know that by the time I get down to 2 bonds and 3 lone pairs, I'm back to a straight 180-degree angle. Let's look at the 3D. So here's my trigonal bipyramid. My phosphorus is hanging out in the middle. I've got fluorines. 1, 2, 3, 4, 5. The bonds, you can see the little triangle that I just drew around the axis, or sorry, around the equator. And now you can see the axials straight up and down. And so that's where your 90-degree and your 120-degree angles come from. Now I want to pay attention here. I notice that the way that the seesaw looks in the next one, with my sulfur in the middle, and I'm going to need to change color, sorry about that, sulfur, and 4 fluorines, my lone pair is here. Do you notice that it came off of the equator, right? The axis, the axial positions are still intact, sticking straight up and down, right? So we remove equatorial first, and hopefully that makes sense, because if I look at my picture here, the equator's more crowded, isn't it? There's 3 atoms around the equator, and there's 2 atoms on the axis. So if I remove from the equator, I reduce my crowding. So I remove from the equator first, and I'm left over. And you can now see that this is a seesaw shape. Look how unbalanced it looks, right? We've got this big lone pair, and it really does. It looks like that seesaw that's left over. ClF3, and I apologize for the typo on this slide, it is most definitely not linear. This is a T-shaped molecule, right? I've taken 2 of my equators, right? 2 equatorial lone pairs, and I've left just the 3 atoms. And when I do that, here's my Cl, here's my F, and my F, and my F. They're flat, right? This is a plane. This is a planar molecule. All those atoms are flat to one another and flat to the piece of paper. So that one actually does work. Let's look at our last set, at our 6 electron domain geometries. One thing I want you to know is that the OpenStax textbook has a couple more. They have a 3-3, oops, and a 2-4. Not worried about those. You don't have to memorize them. They don't really happen often enough for us to care. We'll stick with these sets. So first off, the parent name for this shape is called octahedral. An octahedral molecule, again, has axial and equatorial, right? We're going to put our one in the center. And here's the axials that I just drew, sticking straight up and down. But this time, around the center, I've got 2 atoms coming out at me, and then 2 atoms going away. So I've got 4 around the equator, and then I've got 2 down the axis. What that means is that every last bond angle in this molecule is 90 degrees. So that's not so bad. And if all of them are bonds, like here in XEF6, we call that octahedral. Some books will get lazy and they'll put O sub H. So if you ever see that, that's what octahedral means. When I take away one of those bonds and I turn it into a lone pair, like this, and this is actually a 2+ ion, this molecule with 5 bonds and 1 lone pair is called a square pyramid. And you can kind of see what that looks like. You can see these 4 chlorines at the bottom are the base of the pyramid in my drawing. And then you can see, right, there's a square base at the bottom, and then there's the tippy top of the pyramid up here. That's a square pyramid. We've looked at triangular pyramids, trigonal pyramids, where I had a triangular base of atoms and then one sticking up. Now I have a square base of atoms and one sticking up. Last but not least, square planar. So it's possible to have 2 lone pairs on a central atom, like this platinum tetrachloride, or platinum 4-chloride is a better name for it, right? That's called square planar, and you'll see in the 3D shapes in a moment why we call it that. Here's my 5 electron, or my 6 electron domains in 3D. Again, typo, I apologize. My octahedron looks like this. My sulfur in the middle, my fluorines, and you notice that there's one fluorine just kind of hiding out at the back. Here's my square around the middle, and here's my axial one sticking up and down. On the other hand, this MnCl5 2-, so I had the wrong charge on that ion. 2- is what it is though. You see my Cls, and this should be MnCl, and then my last Cl is misrepresented with the wrong color, but it'll be okay. My bonds now, my manganese is in the middle. 1, 2, 3, 4, and you see the square base of the pyramid? It looks less square as I'm drawing it, first because I'm not a very good artist, but second off because of the 3D arrangement. And then here's my chlorine sitting up, right? I've got square base of the pyramid. And then I've got the atoms like this. I'm not drawing the bonds at this point, I'm just drawing the shape. In fact, I'm drawing everything but the bonds in that picture that I just made. But still 90-degree angles and less than because that lone pair, and by the way, the lone pair is down here in this picture. You notice that we're still taking from the axial, or that we are taking from the axial in this position. And that's because in an octahedron, there kind of technically isn't an axial and an equatorial. It doesn't matter how I turn it, it will always look the same. And you can rationalize it to yourself by turning that octahedron in your mind. It looks the same no matter what. So even though I've kind of pretended that there are axial and equatorial positions, it's not true. Last but not least, I take off my 2 lone pairs, and the 2 lone pairs want to spread out as much as possible. And so there's one sticking up and one sticking down. And what I'm left with is the square in the middle. This is another flat molecule. And those actually are just straight up 90 degrees. I don't need a less than in this case. They're just spread out as much as they can be to share that 360 degrees of space. So again, at this point, you should have yourself a VSEPR table with electron domains and a parent name, number of bonds, number of lone pairs, and then the molecular geometries, which means that you can draw yourself any Lewis structure you want and predict any shape you want. Go and practice that and memorize that table so that you're ready for exams. All right? See you in class.